This is going to be a perspective on where we are in fibre sensing. It's not going to look at any particular technology, it's just going to tell a story and tell it very quickly. Fibre sensing has been around for half a century. What has it done? Where has it got to? Where might it go? I try to give some sort of inkling as to what possible answers to this might be. And the other contrast, of course, is fibre optic communications are everywhere and do everything. But fibre sensing, you know, most people haven't heard of it. Wonder why. What is a fibre sensor? Well, most people here will know, I'm sure. Basically, you take a fibre to a place with light down it, you whittle it something outside and modulate the light, and with a bit of luck, and if I can find the pointer, here we go. What comes out here will change in response to what goes in there. There's always something else coming in, though, to spoil the story. And that's part of the issues. It's there with all sensors. It's not unique to fibres, but it's one of the things which is often overlooked, particularly by rapid publication folk who want to demonstrate the latest refractive index measurements or whatever. And this is what is that in words, basically? A physical, chemical, or biological parameter will modulate the light, and you can either take the light to a zone, you can leave the light in the fibre and modulate from outside, and you hope to get a signal that makes sense thereafter. Who came first? The real question is, does it matter? But it's interesting to reflect on it. That was in Nature talking about tectonic plates just a few weeks ago, and they concluded it didn't matter either. This might be one possibility. Former colleague of yours, actually, I think, Silas, long time ago, but people ignore that. 1954 that came out, well before most people here were born. This one is probably the kind of star candidate for being the first. It's a very simple reflective sensor. It works like this. You have a fibre sending light in and a reflecting point on a fibre collecting light. Change that distance, the coupling between here and here changes. What is interesting about that is that if you're of a mind, you can go and buy one now, and it's quite a nice, useful machine if you happen to want this sort of machine. I don't know how many they sell, or even whether they appear in the fibre optic sensor market statistics, but they're there. This is also a variation on the theme. This is an intracranial pressure sensor, which, as you can see, is churning away at 60,000 units a year. That's the bit at the end, not the head end, since these are designed to be disposable. But it's an indicator of how important it is to have a simple idea, because someone might even use it. The fibre interferometer gets a lot of coverage. Eli Snitzer patented all this sort of stuff way back in 1969. I don't think anybody really discovered that until about 1990. Unless they just didn't want to admit it, because they'd been publishing papers on it as well. But Eli was a very gentle and caring soul, so he didn't worry about such things. There's three different principal sorts of interferometer. There's a Mark Zender, there's the Sagnac, and there's the white light interferometry version of it. And all of these have found their niches in the interim between first appearing, as you can see on the dates there, in the early 1980s, now in the Sagnac case, 1970s. And that was a Sagnac interferometer from a while ago, but that's what one might look like now. And if you're of a mind, I don't know how you test this, but the noise level corresponds to one rotation every 100 years. This is from Mixed Space in France, and is quite some instrument. It's a nice big chunky thing. And this one, of course, you can put in your pocket. And even that will do a degree a second, a degree an hour rather, up to about 1,000 degrees a second. And you can see the size of it. That's a US quarter, roughly the size of our 10p pieces. This is white light reaction. And again, this one's been around for a while. Originated out of EPFL in Switzerland. And over the last 3 decades, we've got several variations on this particular theme appearing through rock test in Canada with Smartec. And one thing that's in common with all these achieved things, or 2 things really. One is the user doesn't really know that this is fiber optics. And the other thing is that most of the endeavor has got nothing to do with the optics. You've got to package it, you've got to signal process it, you've got to get it approved by the authorities, and a whole bunch of other stuff as well. We started with networks in the 1970s as well, in 1980s, so this is an early paper on networks. What I liked about publications in those days is that they hadn't invented PowerPoint. So you could draw things on the back of an envelope and get them published. It was much quicker, honestly. And you see the wavelength multiplex system and the time division multiplex ladder system, both of which are, so all 3 of those are still in use. In things like this is a highly multiplexed interferometric system. Don't know how clear it is, but there's $140 million went into making this all happen in the US. It was launched quite literally a couple of 3 years ago. Difficult to read this one, but this is about phosphors on the end of fibers. The phosphors are one example of sticking things on the end. This was to measure temperature. You can also put variations on the theme to measure chemical phenomena and so on. And that was patented in 1978. You can also still buy it, which is quite an achievement for Luxton stroke Lumasense to still be around and making things. Fiber optic current monitoring's been around for a while as well, and that's now a settled commercial product. This has something special, which is that it's a very obvious one, but you don't need a piece of wire that goes from there to there. You can do it with fiber, so you don't have to worry about insulation and big long what they call plastic things, you know, the insulators. It's all done relatively easily. But one that's had the biggest impact as a single technology is probably this, with distributed sensing. The idea is straightforward: modulate the input light, the light's modulated by the measurand, and you process the signal. Again, this has been around since the 1980s, and now it's found lots of application. Fire in tunnels, there's quite a number of these on London Underground, for example. This is pipeline monitoring from Omnisense. This one is from the paper by Henry Taylor, about 15 years ago now, 10 years ago, on the initial, or at least he thought it was the initial Rayleigh backscatter, but it's essentially a variation on the polarization version. And you get messy looking traces which you have to interpret. Back to the old theme of signal processing needed, presentation of data to the user needed. But again, a unique thing from, well, this is just, if you want to watch this, watch it on YouTube. There's quite a lot of them around. Look up any of their websites, they'll take it to you. This is a truly unique sensing system. You can measure temperature to a degree or so, or possibly better if you work hard, up to 50 kilometers and more. You can measure strains up to 100 kilometers. You can measure acoustics and vibration up to 20 kilometers or so, depending on how you work it all out. So there's a lot of benefits there that aren't available using any other technology at all. And the last arrival, I think, was the Bragg grating as a sensor, though it actually started in 1978 with Ken Hill and company. Sensing appeared about 10 years later. That was with Jenny Meltz and so on. And the idea, again, most people here will know about this. You put the grating and the fibre, reflect different wavelengths, change the wavelengths with strain and temperature, and you can make big arrays of all these things, up to thousands of sensors, and indeed there are things with thousands of sensors on them around and about. One issue which is common to certainly strain sensing and a number of others is here. Lots of talk about putting things into embedding into composites, but remember, there's your fibre, the measurement's right in the middle, and in there's something sticking it together. And if you get it wrong, you get, instead of a nice, well-behaved fibre grating, something like this, which means, again, very careful on the packaging. But there's a number of them around. These have been installed for some time now. That's been in trial system for some time. I gather rumours from the US that they're beginning to be approved for aerospace use. These are used on some of the wind farms that you'll see around and about, and Moog is quite optimistic it'll be used in more wind farms. And there's lots and lots of other applications floating around. This has been physical parameter sensing. Very quick, very, very quick look at it. If you look at fibre optics, you can of course take light to awkward places and perform spectroscopic measurements, and that's just absorption spectroscopy in a very schematic form here. You can use Raman, you can use laser-induced breakdown, and all of these have been done in various forms. And you can, this is a bit like the phosphor we saw earlier, you can stick things on the end. Or you can make networks, and this is a network of gas sensing systems with control units and a range of up to 20 kilometers and about 300 points off one single laser, which is quite something. And there's a couple of examples of this in action. This is another spectroscopic system from Anna Mignani, looking at olive oil. It's also, let's just bring a Scottish flavour to it. We did do a paper on whiskey a little while ago, characterised using this system, and it combines scatter and transmission spectroscopy. So there's lots more going on, as well as you can see here. Right. The basics have been around for a while, though, and I would offer that most of the basics were settled about 1990 or thereabouts. And if you want to have a nice history of fibre sensing to that time, there's a 700-page tome from Ralph Kirsten and Rainer Wilsch, which is available. So what we got with fibre sensing, we have an awful lot of application sectors. We have an awful lot of ways of modulating light. It gets very confusing, this. We have all sorts of different architectures that we can play with. So there's lots of technical flexibility, and there's quite a number of application advantages. These are all well rehearsed, and I'm assuming that most people in this room will have used these to tell a story to some potential sponsor or other at some stage. So what's happening now? And we'll look a little bit, very fleeting, into the rest of the talk on the market, the technologies, and I think possibly the most important part of optical fibre sensing is the people who've come through it and what they've done. There's the market. It's less than about 2 billion in 120, certainly less than 2%, possibly even less than 5%. That's the, and don't ask how you measure this. I have no idea. But there's the sort of numbers you see published. What for the future? Well, there's one that was published in about 7 or 8 years ago now. As you can see, it's a relatively small amount, even if it does get to 5 billion a year. The market surveys that are more current, you can take your pick. Typically, say about 4 billion per annum in 2025. We'll see if we're around still. And there's some agreement that the growth is going to shift from physical measurements of oil fields into other sectors. Another issue, and I put this up not because it's a current number that's relevant, but look at all the different colours on here. Each one of those colours represents a different application sector, which represents a different package, a different bit of software, a different customer, a different set of standards and rules to abide by. So it's quite difficult to keep up with all that. So why is it so modest, this impact? Why hasn't it been a big, we've seen all the benefits, for goodness sake. Humans are skeptical buggers. That's the basic problem. And if you think about what's involved, you see, getting there, as we've mentioned many times already, involves all this sort of stuff and probably more. And I'd like to emphasize to everybody that writing the paper about it was the straightforward bit. Making it actually work is a much more tedious and actually a rather interesting task. So what do? Here's your idea in the lab. You put it together in the lab, and you might be able to find some partners and do a field trial. The partners might include a user, and the user will compare with computing technologies. Now, I put the canary on because it's actually inside this century when one particular deep mining nation of a definitely developed kind took the legal requirement for having a canary down the mines away about 2005. So that's caution and skepticism for you. If the user's convinced, and or not convinced, one of two things can happen. If he's not convinced, you go back into the comfort zone. If he is convinced, then you go into a very uncomfortable zone, which includes standards, manufacturers, regulations, test procedures, installation, a whole bunch of other stuff. And you here need to be able to talk to these folks in a language they understand, and communications is critical. It takes time, and these are some maps of various sectors from Alexis Mendes, but this is the exploration and production of oil and gas, and you see to 50% penetration in 3 decades. Patience, please. And one of these interesting things to look at is the fibre drag grating against the strain gauge. Drag grating has all these lovely things going for it. The strain gauge doesn't have much going for it, but everybody knows it. And not too far from here is the Queensferry Crossing, which was opened by the Queen a few weeks ago, no, a month or so ago. Lots and lots of sensing on it. In fact, if you look at these racks under the bridge, these get filled up with cables as much for sensing as they do for power and lights and communications. This guy is one of our former students. He was in charge of sorting out the sensing systems. Obviously, he knows about Bragg gratings. It's got all these advantages. There's 400 sensors, 3,000 Bragg gratings. Campbell went for straightforward strain sensors for very good reasons. And I won't bore you with them, but I had long discussions with him about it. And he was, I think, quite correct to do that. It was a good professional decision. If you're interested, I'll bore you with more of it later. So what about the future? Well, OFS, like everything else, you have social drivers and new technologies. Social drivers, there's a lot of them. Photonics 21 puts out a list. It's 2011 it came out, it's still the same. And here it is. Even older list comes out the National Academies of Engineering in the States, but that's still there from 2008. So when you look at this, you think, well, there's quite a lot of areas into which we can contribute with fiber sensing. And certainly there are opportunities in there. And there are new applications. So I think there's interesting things to come. And these are just a few examples of what you might be able to do with fiber sensing in those sectors. As far as I'm aware, very little of this has been addressed thus far in terms of even proof of principle. What do we need to do to make this happen? You have to understand what the user wants. You have to understand fiber technology and translate it. You have to work out whether it's worth doing it. And you have to make the whole technological base that exists more visible and more credible to current and emerging technology companies and markets. And it's back to communications. This communications thing is very, very important. If you go to new technologies, you come to similar things, all sorts of things around to modulate those parameters that we thought of before. And some examples will be coming later on in here. Here's one example. This measures refractive index and temperature on a fiber end using some etched fiber techniques. There's also integrated optics around, and custom-made integrated optics is emerging. This is just one example. The basic thing, though, is to get the signal-to-noise ratio better. There was some of that in the last talk, I'm sure. And you have three options: more power or less noise on the source, better sensitivity in the detector, or improve the interface between the measure and the optics. The source, you can squeeze light. Now, in the previous talk, I'm sure I didn't actually come to the first bit, I must admit. There must have been something like this there, the optical squeezer in LIGO. It's not very compatible with what we like to do, but these perhaps are. The trouble is you only get half a dB or a dB from these. When there's some micromechanics which does the same sort of thing. Lots of things you can do to enhance the interaction. Slow light, or some people like to call them resonators. In other words, you just keep the light in contact for a wee bit longer. You can take this to a silly extreme, and this was published in Nature just a couple of months ago, where you have resonators that are so coupled together and so unstable that even the slightest sneeze in the room next door will do something to them. There's microstructure fibers. There's been quite a bit of work on looking at different shapes mechanically, and also concentrating the ramen or the bouillon and suppressing the one with respect to the other. There's also been some work on holy fibres, and among other things, the Kerr effect in gyros can be reduced considerably, and the hole can be used as a host for a spectral study and absorption spectroscopy in gases. This I got literally yesterday, but this is a publication coming very soon in Optics Express on a distributed gas sensing system using hollow core fibres. Use different fibre materials. This is some work with spider webs. It looked kind of intriguing, but it doesn't seem to have got tailed before thus far, but it still looks intriguing. Polymer optical fibres, you can hear quite a bit about those. There's nanophotonics, and you'll hear much of this in this meeting as well. Put things on the end of the fibre and make a multi-channel chemical sensor. You can make optical antenna arrays and focus light and send it around and so on. This is an example of an extreme of that. Now, a fibre diameter, that's the diameter of a single mode fibre from about there to there. So you can work out how many antennas there are on it. There's metamaterials. Could you put a metamaterial on the end of a fibre and have a perfect focusing system? I don't know. And then you've got lots of tiny points focused on the test sample. So, finally, what have we got after all that? That's been a very much a rush through, I admit, but it just gives you some feeling as to the sort of things that have been going on, the sort of things that might go on. The optics is undoubtedly fascinating. 50 years later, we've got modest penetration in the sensor market. Distributed architectures, including Bragg gratings, have done the impossible, and gyros and voltage and current sensing do what was possible, but much better for various reasons. For the future, there's new photonics, and there will be more demands from society for fancy sensing. Of that, I don't have any doubt. And I still think it's a magical area for students to study, because it's highly multidisciplinary. It has all sorts of bits of basic science in it, and you have to do it properly, you have to be able to communicate to quite a diversity of people. And I would argue that perhaps the most useful outcome is the students who've gone through the experiences. And looking at the way our students over the years have developed into a whole range of things, most of them nothing to do with fibre optic sensing, I think that's actually a good tribute to it. Similar points here. Research is good. Practical realization, I believe, is still necessary in some form. And most of all in that, you need to be able to communicate, understand, and listen. And I think that has been quite fun as well. So thank you.